Alright, welcome back to my channel. So today in this video I will be talking about the curves, which is in the differentiation chapters. So in the first one you learn about the gradients of a normal and gradient of a tangents. As this one I already explained in the previous videos, as you can revise back in the previous video. That is, the important concept is m1, m2 equals to -1, where the gradient of the tangent times the gradient of the normal equals to -1. Here is the important concept to find the equation of the normal and equation of the tangents. And okay, the second one is the stationary point or turning points. These two are actually the same thing. So why I say it's a stationary point? As you can see, let's say we have function as shown as this curve I drawn. So let's see. So at this curve we got few points that is like, how can we say, like I going here and I turn to another direction and I turn here, then I go here, and at this point I turn, and here at this is the peak, here is the peak, and then I turning down and here. So at this turning point or stationary point is when the dy dx equivalent to 0. So why dy dx equal to 0? We know that dy dx represent as the slope or gradient, means that how concave or how slope is the, as you can see how slope is my line is going here or here. So now you can see at every point here the gradient is actually a straight line. It's not like that. This is not like that. It's all straight lines. So they are not slope at all. That means their gradient is 0. So if you want to find the stationary point or turning points, we are using dy dx equals equivalent to 0. So at these few points I would like to explain their name also. So in here is local maximum, and this is local minimum, and here is local maximum. As you can see along the curve, here is the lowest point, so we call it as absolute minimum. We can have many local maximums, but we can only have one absolute maximum and absolute minimum. That means it's the highest and the lowest peak of the curve. So here is the absolute maximum, and here is local minimum. Alright, so it's here we all learn about this equation. So to find all these points, we are letting the dy dx equivalent to 0. So we can get many points of x, y. Let's say we get x1, y1, x2, y2, and we must give all the answer in the, we must give all the points in the answer. Alright, so now the third concept is the increasing and decreasing. So we know about the slope is derived as dy dx. So now what is mean by dy dx greater than 0? So we know that dy dx is actually the slope or the gradient. So it's how slope is the line, you can see. So if here is the gradient dy dx equivalent to 0. So when greater than 0 means that it is going upwards. So it's positive. When it's negative means that it's going downward. Like it's just like the y-axis. It's just like the graph y equals x, positive x, and if y equals negative x, it's like here, y equals negative x. So here is the dy dx, negative dy dx, and here is the positive dy dx. So when we see the dy dx is greater than 0, means that the slope is going upward, whereas here when there's the smaller than 0 is going downwards. So one important point is that the stationary points or the turning points divide the curve in an alternate at the increasing and decreasing intervals. Why I say like that? So let's see. Exception for inflection point. So what is inflection point? I will explain later what is inflection point. So we can see increasing or decreasing. Why? Stationary point. So let's say in this case, this point and this point are actually stationary points. Stationary points. So we have two stationary points, and let's say we brought a imaginary line here and here. You can see why I say that stationary divide the curve into alternate increasing and decreasing interval. As you can see, here the slope is going upward, right? It's going in the positive direction, so it's increasing. So if you find the interval about here, about values of a range from 0 to x1, let's say, if you get the dy dx is greater than 0, whereas after the turning point, you can see the slope is going downward, so the dy dx is actually smaller than 0, and here is decreasing. And if you find the dy dx at this interval, we will get the dy dx is actually smaller than 0. And now another turning point is going up again, so the dy dx is again greater than 0, and this is increasing. And you can see here, so is the turning point or the stationary point differentiate the both cave. There is concave upward, here is the going upwards, and here is decreasing function, is increasing function, decreasing function. Yeah, it just like alternate. Yeah, if we separate the curve. Alright, for the concavity, for concavity we will analyze about the d squared y dx squared. That means it's the second derivative. So I hope you all know what is the second derivative. So let's say I have y equals to 3x squared. So the first derivative we will get 6x. And the second derivative we will differentiate this term the second time with respect to x, and we will get 6. Alright, so when we determine the d squared y dx squared, when we get the answer is greater than 0, we will get the concave upwards curve. So we will get a pattern like this. And if we get is more than 0, we will actually know is concave downwards. So the turning point is here, and here is concave downwards. So it's implied from the local or maximum minimum point. However, we will learn how to do it later in the example I showed. So note that the point of inflection will divide the curve into the alternate concavity. It means that after the point of inflection, you will know that there are alternate concavity that is concave upwards and downwards after the point of inflections. Let's say I have a curve like this. So here, yeah, I draw nicely. So here is actually point of inflection. Yeah, you can see. And here, the curve is actually like concave downward, right? But after the point of inflection, you will notice that the curve is actually going upwards. It's pretty like concave upward, right? So it's concave upwards. So that is why we call it at point of inflection. This is not belongs to the minimum point or maximum point. It's called a point of inflections. So for point of inflection, to find it, we are not analyze dy dx. Here is not important here, but we are analyze the d squared y dx squared. That means the second derivative of the function. When we want to find the point of inflection, we can find d squared y dx squared equals to 0, and we find the x value and y values. So, however, if we only satisfy one of the conditions, that is not true. We need to satisfy the second condition. So the condition is and. Both conditions must satisfy. So we must analyze the both conditions so that if my d squared y dx squared is equivalent to 0, while my d cubed y dx cubed is not equal to 0, hence at the point xy is called the point of inflections. So actually we can notice it by dy dx. I will teach you in the example later. So yeah, here is a point of inflection. You can see the change of concavity from concave downward to concave upward. You can see from y equals to x cubed graph. So if y equals to x cubed, you know the graph is like that. So and hence, and point 0, 0 is the point of the inflections. Why? Let's say I have y equals to x cubed, and here is the graph, and I differentiate it, I will get 3x squared, right? So I need to determine d squared y dx squared in order to find the point of inflections of local maximum minimum or the point there. So I will get 6x. So in order to find the point of inflection, for point of inflection, we know that d squared y dx squared will equivalent to 0, right? So now 6x will equal to 0, x will equal balance to 0. So when x equals to 0, y equals to x cubed, 0 cubed, and we get 0. So the point is 0, 0. So we already satisfied the first condition, that is d squared y dx squared equals to 0. And now, to check is either this point is the point of refraction or not, we need to differentiate third time. So we get t cubed y over dx cubed, we get, when we differentiate the 6x, we get 6. Alright, so 6 isn't 0. So we know that 0, 0 is point of inflection. So you can plot the graph is